Then, hello everyone. It's my great pleasure to welcome all of you to the restart of our international online seminar on intermal methods in control engineering. It's a restart after the summer break. And in fact, we're celebrating today the 4th anniversary of the seminar. And yeah, it's my pleasure to welcome today one of our former exchange students at the University in Oldenburg, Damien. And yeah, let me introduce him. He received a double degree in autonomous robotics from ENSTA Bretagne and in dynamical systems and signals from Polytech Angers, both in 2023. And since then, he's a PhD student at ENSTA Bretagne in the Lab-STICC laboratory. And one of his research activities are also directed towards the presentation that he'll give us today, namely bounding the success probability of an uncertain event in a probabilistic world. Damien, the floor is yours.
Okay. Thank you, Andreas. Just to be sure, do you hear me? Do you see me?
Yep,
Okay,
everything working perfectly fine.
Okay, perfect. So hello, everyone. Again, thank you, Andreas, for this introduction, but also for inviting me in your online seminar. Today, in this presentation, I'm going to present you my work on the bounding of the success probability of an uncertain event in a probabilistic world. So let's start with a little bit of context. I am a PhD student at the Lab-STICC laboratory at ENSTA Bretagne in Bretagne in France. I am under the supervision of Professor Luc Jolin, of Dr. Simon Roux, and Dr. Fabrice Lebar. And I've got a funding from the AED, which is the innovation agency of the French Defense Ministry. So the reason behind this funding is because my thesis is mainly dedicated to naval mine clearance applications. And the technical challenges in naval mine clearance application are the low-cost navigation and the guaranteed mission planning. And so the goal of my thesis is to reach and to identify underwater objects with low-cost robots as reliably as possible. So first, let's talk about naval mine clearance, and we start with the definition. So naval mine clearance is the practice of removing explosive naval mines using various measures to either capture or detonate the mine. The success of a naval mine clearance mission is generally determined by the validation of an event based on set assumptions. It can be, for example, the coverage of a given area by a sensor. You have an illustration on the left on the figure 1, where a mine hunting AUV, represented here in yellow, is following a reference trajectory, represented here by the blue line, and using a side scan sonar, represented by the red area, and cover an area on the seabed. And so the area covered by the sonar is represented in gray. And we have also the avoidance of a forbidden area. So first, let's take an example of a typical naval mine clearance mission, which is identifying an object lying on the seabed. So to model this problem, we propose to have a punctual object which is lying on the seabed. So the seabed is a 2D plane and the object is punctual and represented here by the red circle. We have an AUV for autonomous underwater vehicle, which is equipped with a camera which must take a photo of the object. So the camera have a given field of view and a given detection range. And so the area covered by the camera is represented here in green. To carry out this mission, the robot will follow a non-trajectory, which is represented here by the black dotted line. And so as the robot moves forwards and follows the trajectory, the area covered by the camera increase and is represented here in green. And so at the end of the mission, we have covered a given area. And to know if we succeed in the mission into identifying the object, we only have to check if the object is inside the covered area or outside. If it's inside, it is successful. It is outside, it is a failure. So which means that the mission success can be described using a binary variable, so it can be true or false. However, this model is too far from reality because in an operational context, the position of the objects to be identified is rarely exact and is subject to uncertainties. In this work and for this presentation, we propose to use intervals to represent this uncertainty by bounding the object position into a box, which means that all the possible positions of the object are contained inside this box. So we know that the object is inside the box, but we don't know the actual position of the object. So if we go back to the previous example, this time with an uncertain object, so with an uncertain position, but bounded into a box. So you can see here, this is the actual position of the object. I don't know it, but I know that it is inside this bounding box. So we have again an AUV, which is equipped with a camera. It will follow a reference trajectory to carry out its mission. And so as the robot moves forward, the area covered by the camera increase. And again, we covered a given area at the end of the mission. And this time we have three cases. The first cases is the cases where the bounding box is entirely inside the covered area, which means that we have covered all the possible position of the object. So we can guarantee that we will be able to see the object during the mission. But if the bounding box is outside the covered area, it means that we are not able to see at least one possible position of the object. So we can guarantee that the mission will be a failure, will not be able to see the object. And in this case, where the bounding box is inside the covered area but also outside, the result is uncertain because we only cover a small part of the possible position. So in some cases, we will be able to see the object, and in other cases, we'll not be able to see the object. And so in this case, it means that now the mission success can be described by a three-value logic variable. So it can be true, it can be false, or it can be unknown. To carry out this dangerous and complex mission, the use of autonomous underwater vehicles has gradually become the norm. AUVs are equipped with sensors to gather information about the state and the surrounding, but these sensors are also subject to uncertainties. And the most usual way of modeling AUV sensor uncertainties is to use probabilistic assumption. For example, we can make the assumption that the sensors have a wide Gaussian noise on the sensor measurements, and it leads to a probabilistic navigation. So an example of probabilistic navigation is the case of an AUV with a noisy compass. So we have an autonomous underwater vehicle which must follow a desired trajectory, and to do this it is equipped with a compass. So the robot here is the AUV and the trajectory here is the desired trajectory. However, the compass is imperfect, which means that the estimation of the robot's heading is noisy, making the robot behaviors random, which means that we can have several possible trajectories for one mission, and they are represented here in gray. There is, in reality, an infinite number of trajectories. And so the robot actual trajectory will be one of the possible trajectory, and this trajectory will be drawn randomly at each new simulation. For example, if I launch a simulation here, I will have one of the possible trajectory that will become the actual trajectory of the robot. And so this is the challenge. So in a mine clearance mission, we have to deal with a probabilistic navigation, and we have to deal with uncertain events, and we want to know how to estimate the success of a mine clearance mission. And to do so, we propose to implement and to use a Monte Carlo estimator adapted to the three-value logic that I will call in this presentation interval Monte Carlo. So first, let me present you what is a Monte Carlo estimator. So a Monte Carlo estimator is an empirical and unbased estimator of the expectation of a random variable. So here, the Monte Carlo estimator mu of n for a random variable x can be expressed as the following one. So we need, this is why it is empirical, we need sample of the variable, and by averaging this sample, we can converge to the expectation of x. And it is unbased because we know that the expectation of the estimator is equal to the expectation of x. And so according to the law of large number, the more n will tend toward infinity, the more accurate the estimator will be. But in our case, we don't want just to estimate the expectancy of a variable. We want to estimate the occurrence probability of an event. And so we can adapt the Monte Carlo estimator to do so. So a Monte Carlo estimator of an event E and for a random system S can be expressed as the following. So still, we need a simulation of the system S. And for each simulation, we will compute the value of the delta E function, which can be interpreted as the occurrence of E in the simulation. So if E occurred in the simulation, then a delta of E of S will be equal to 1, and it will be equal to 0 if E didn't occur in the simulation. And by averaging this value, we can obtain an estimate of the occurrence probability of the event E. And still, according to the law of large number, the more n tends toward infinity, the more accurate the estimator will be. We can apply that on our example. So we will still want to identify an object lying on the seabed. So we have a punctual object which is lying on the seabed, which is the seabed is a 2D plane. We still have an AUV equipped with a camera which must take a photo of the object, but this time the position of the AUV is uncertain and described by a Gaussian distribution. So it is represented by here by a confidence ellipse and a mean. So we generate sample of this distribution, and for each sample of the distribution, we'll check if the object has been seen or not. For example, for the first sample, we can see that the object is inside the covered area of the camera, and so the value of the delta E function for the first sample will be equal to 1. If we take the next sample, we can see that this time the object is not inside the covered area, which means that we are not able to see the object. So the value of the delta function for this sample will be equal to 0. And if we take the last one, this time the object is inside, so the value of the delta function is equal to 1. And by doing so for all the sample and by averaging this value, we obtain an estimate of the occurrence probability of the event, which was to see the object during the mission. So in our case, we want to deal with uncertain event, which means that we have an uncertain realization. So the realization of the event can be true, false, or unknown. And so we propose to adapt the Monte Carlo estimator to a 3-value logic using intervals. So the Monte Carlo estimator become an interval, which is interval mu of n. And for an uncertain event E and a random system S can be expressed as the following one. So still we need simulation of the system. And for each simulation, we will compute the delta E function. But because the event is uncertain, the realization can be guaranteed true, can be guaranteed not to happen, so false, or can be unknown, so 0, 1. And so for each simulation, we'll check if E is guaranteed to happen. If it's the case, it will be equal to interval 1. If E is guaranteed not to happen in the simulation, then it will be equal to interval 0. And if E is uncertain, then it means that we can say if it will be false or true. So we take interval 0, 1. And by averaging this value, we can bound the success probability of the event. So if we go back to our previous example, this time with an uncertain object, so still this is the actual position of the object. We don't know it, but we know that the object is inside this bounding box. We have an AUV equipped with a camera, which must take a photo of the object. The position of the AUV is uncertain and described by a Gaussian distribution, which is represented by a confidence ellipse and a mean. And so we generate sample of the distribution, and for each sample, we check if the bounding box is fully inside the covered area, is fully outside the covered area, or is partially inside the covered area. In this case, the bounding box is fully inside, which means that we can guarantee that the robot will be able to see the object. So the value of the delta function will be equal to interval 1. For the other sample, this time, the box is fully outside the cover area, so we can guarantee that we will not be able to see the object, so the value of the delta function will be equal to interval 0. And for another sample, this time, the bounding box is partially inside the covered area, which means that in some cases, we will be able to see the object, and in other cases, we will not be able to see the object. So the realization of the event is uncertain, and therefore, the value of the sigma function will be equal to interval 0, 1. And by averaging this value, we can bound the occurrence probability of the event, which was to see the object during the mission. So we propose to apply this in a more complex scenario. So we have a robot equipped with an omnidirectional camera, which means that it can see at 360 degrees, and which enable it to identify objects on the seabed. So the robot is represented here. The camera have also a detection range. So the detection area of the camera is represented by a circle. To carry out its mission, the robot will follow a reference trajectory using a noisy compass. And three uncertain objects, are placed on the trajectory. And so again, this is the actual position of the different objects, but we don't know the actual position. We only know the bounding box. So we know that the objects are inside this box. And we want to know so the aim of the mission will be to identify the 3 objects during the same mission. And so we want to know the success probability of such mission. So concerning the robot modeling, we can modelize the robot with a state equation, is this very one. So it is a Damien car, but we have a noisy compass, so we have the noise on the heading. And we have initial state that is given here. So here is the starting point, so it is the initial state of the robot. And here is what I call the reference trajectory. So it's basically the trajectory of the robot when the noise on the trajectory is equal to 0. So we will generate sample and simulation of the system for a duration of 20 seconds and a time step of 0.05 seconds. In this case, we will generate 10,000 trajectory. So here we have 1 trajectory in blue. Here we have 10 trajectory, and at the end we have 10,000 trajectory. And now we have to check for each trajectory if the mission is succeed or not. So here will be the position of the different objects or of the different bounding boxes. So they are placed around the trajectory. And so for each trajectory, we'll check if we see the object or not. So for example, for this one, the mission is a success because we were able to see the 3 objects during the mission. The 3 bounding boxes were inside the covered area of the camera. So we can decompose that. So we were able to see the first object, the third object, and the last object, the second object, sorry, and the last object. And so the global realization of the mission is equal to 1. For this sample now, so here we are able to see the 2 first objects, but we were not able to see the last one, which means that the mission is a failure because we were not able to see the last one. And so the delta E function for this simulation is equal to interval 0. And a last sample here is uncertain because we are able to see the 2 first objects, but in this case, the bounding box of the third object is partially inside the covered area, which means that in some cases we will not be able to see the object. So the realization of the mission to see the 3 objects in the same mission will be uncertain, and therefore the value of the delta function will be equal to the interval 0, 1. And so result of this simulation, we were able to bound the occurrence probability of the event, which was to see the 3 objects during the same mission. We were able to bound this probability between 37% and 71%. And this result was obtained with 10,000 trajectory. Here, represented here, you have still the reference trajectory with the black line. The green line has the generated trajectory for which E is guaranteed to happen. The yellow line generated trajectory for which E is uncertain, and the red line is generated trajectory for which E is guaranteed not to happen. And so we can also determine the probability to see each object individually. So the probability to see only the first object is between this. We bound the occurrence probability to see the first object in this interval, for the second object in this interval, and for the last object in this interval. And so we can see that in this mission, the problem is to explain why we have such uncertainty in the mission is because the third object have a high uncertainty of occurrence. And we can ask about the convergence of the interval. So here is the evolution of the bounding interval of the success probability. And so we can see in red the upper bound and in blue the lower bound, and we can see that after 4,000 simulation, the interval has converged to a value, and so we can suppose that we have converged to the true value of the occurrence probability. We have found a ground bound of the occurrence probability. And so some perspective and improvement. So a way to improve accuracy in this Monte Carlo estimator could be to bisect the bounding box. Indeed, for a given bounding box, we will be able to bound the occurrence probability of the event. And what we can do is bisect this box. For each box, compute and bound the occurrence probability to see this box, and assemble this interval of probability using the union to get the bound on the occurrence probability to see the whole box. and it can have an application to path planning. For example, if we want to do path planning between C marks which are uncertain, we can compute the cost of each branch. So we can compute interval of probability and find the best path to go from the start to the goal with the best probability. So if you have any question, I'm ready to answer.
So many thanks, Damien, for a very interesting presentation, and I'm pretty sure there will be some questions. Who wants to start with asking something? Okay, if there is someone, please unmute yourself. Jelke?
Yes, hi. I have a question. Actually, what happens if the bounding box is larger than the surveillance area of your vehicle?
Yes, so if the bounding box is larger than the surveillance area, it means that in the best case, we will be uncertain and not guaranteed. So the bound will be really uncertain. So we will have a interval with a big width. And so the best thing to do is like to bisect this box into smaller box to improve the accuracy of the estimator.
So that means that even if we take then several passes over the larger bounding box, covering all the area of the bounding box, we can never reach a certainty of 100% that we have found the object.
No, we cannot. But if the bounding box is too big, the estimator will be really pessimistic, will be really pessimist, and the best thing to do is to bisect this big bounding box to improve the result and to improve the accuracy. But yeah, if you can only see with the camera at 1 meter and that and the object uncertainty is too big, it is normal to have a big uncertainty and to not succeed in the mission.
Yeah, so I understand that if you have just one go, but if you can, as in the first figure with the plane that you showed, that you can take
Alors,
a route over the whole area.
so the first figure in which part? Sorry.
The first figure, there was a plane showing I think it was way at the beginning.
At the beginning, okay.
I
Yeah,
think
one
it
of the
should have been
first.
either 26 or something close to that.
So tell me when you find it. This one or?
No, right at the beginning. One of your first slides. Yes, this go further.
So in the case of uncertain object, this one?
No, further on. Further. Yeah. Okay. I don't. I saw the figure, but I cannot see the page number, so I don't know. So I mean that you have your vehicle and you have a large bounding box and you can like make a trajectory going over and over the bounding box in meandering, how's it called? Ein meanderndes Muster.
Yeah, this was a search pattern that you had at the
Yeah,
very
yeah,
beginning
so
of the
okay.
talk.
Yeah, so you're covering the whole bounding box with a search pattern, but
Yeah.
since your field of view is smaller than the bounding box, you can never reach a certainty of 1 that you covered all of the bounding box.
Yeah, if you want to improve, the best is to use a searching pattern. But I'm not sure to understand the end of the question.
Yeah, okay. It's okay. I was just thinking if that makes intuitively sense that you can never cover the bounding box with a high probability regarding of the surveillance pattern that you're taking.
I think Jelke's question is a little bit directed into that direction, whether, yeah, or how to use your quantification procedure to improve the planning algorithm of the search pattern.
Yeah, you can use that to improve for sure. It will be I don't have the name, but you can use it as an estimator to improve your path planning. It can be a good way to do that.
Okay, thank you.
Okay, further questions? In fact, I directly have a question related to the slide, and that's the reason why I remembered the slide number.
Yeah.
What you discussed at the moment is that you say you have uncertainty in your mission. And this uncertainty can definitely come from different facts.
Mm-hmm.
One is you have external disturbances acting on your robot,
Yeah.
wave, and other phenomena. You will also have definitely some sensor inaccuracies,
Mm-hmm.
especially if you have sensor noise and implement a feedback controller. They propagate through the complete control strategy. They
Yeah.
make the control signal uncertain. Uh, do you have any idea whether, let's say, the outcome of your quantification scheme could also help to robustify the controller in order to make the set of possible trajectories tighter?
For now, I don't know. To be honest, we are trying to look at that with Luc currently, but for now, I can't have the answer.
Yeah, the reason why I was thinking into that direction
Mm.
is because what you presented is, let's say, a small ingredient of something that could be interpreted as a mixture of set-based and stochastic SLAM algorithms.
Mm-hmm. Yeah.
Yeah, and if you're learning a little bit more of the environment at runtime, I
Yeah.
think you would have to turn this into a real-time procedure somehow. I think it would not be enough to do this fully offline. Maybe you would gather information at runtime online and then to enhance also maybe the feedback control law.
Yeah, it can be a little bit complex because I'll just I lost the slide up. If I go back here, in the simulation and in this work, we dissociate the navigation and the mission part in the way that we are doing dead reckoning, and we are not using like the object to relocate ourselves. It complexifies the theory, and we are currently trying to look at that with Luc.
Yeah. Okay. Yeah. That's, I think, a very nice and also definitely promising outlook what you mentioned. The other question that I had was at the very end when I think you also answered this to Jelke when he asked his question, the subdivision strategy. If you're
Yeah.
subdividing with interval boxes, that's easy.
Hmm.
Would it be helpful to also use other fundamental shapes for those bounding boxes? You could imagine, for example, sonotopes or whatever.
Hmm.
Yeah, the problem of subdividing a sonotope is typically you get overlapping sonotopes.
Yeah.
But would it be somehow helpful to replace this axis-aligned box by something else?
For the idea of bisecting here is to reduce the size of the box because like sorry, I forgot your name. So the person was asked me a question just before.
Yeah, it was Jelke.
Jelke, sorry, thank you. So if the box is too big for each sample, for each simulation, the result will be always it's uncertain. So we just have a probability between 0 and 1, so it's not really useful. And so the idea of bisecting is computing that on smaller box and to reach a box that is smaller than the covered area. And with that, we can have a better approximation of the success probability. So if in case of zonotop, by bisecting zonotop, you obtain a bigger zonotop, it is not useful. So for now, boxes are, I think, the best thing, but maybe we can look at that in the future.
Yeah, they do not necessarily become bigger. The thing is, they
Ah, okay.
become overlapping. And
Okay,
then
well,
the problem is what you have at the end. You
yeah.
have overlapping
Ah, okay, no,
sonotopes,
okay.
and that means you have at least some parts that are covered twice. You don't have
Yeah,
the simple union formula that you have there in the upper right corner of your slide,
yeah,
but you have
it's not working.
to subtract again parts
Yeah.
of the regions that are counted just twice in the evaluation of your probabilities.
So yeah, you're right. This equation is not good for the top. You
Yeah,
have, yeah. Okay.
yeah, but yeah, it could be interesting to have some other shape. For example, if you know that an object is somehow aligned in the direction of your path,
Hmm.
yeah, that you want to take into account for whatever reason
Yeah.
correlations between different position variables, then it would be helpful maybe.
Yeah, it can be useful because like in reality, the box is maybe not the best way to modelize uncertainty on object position. depending of the sensor and a lot of parameters. So yeah, exploring new shape can be interesting.
Okay, any other question from the audience? If not, I have a very final one.
Yeah.
Just 4 slides back, 65.
65, okay.
No, it was not 65. The thing where you had the individual probabilities for the, no, I think it was earlier. Yeah, this one. Yep.
Okay.
64, yeah. What you have done here is you asked the question whether you have seen all of those objects.
Yeah.
That means, in fact, the formula in this black solid box is more or less the product of the 3 interval probabilities.
Yeah, it is clearly a product. It is a composition of end of a 3-value logic.
Yeah. Yeah, the question that I have here is, how difficult would it be to generalize those expressions also to the case, let's say, that I've seen at least one or at least 2 of the objects? Is this just a generalization of those truth tables then that you have shown here for the
Yeah, I
3-value
think it's
logic?
just like the 3-value logic, and it corresponds to the end operation. The probability. If we want to have seen the 3 objects, it is 2 end, 1 and 2 and 2 and 3. And so by composing with end, it is like the operator of the 3-value logic. So I think it is quite general.
Okay. Yep. Perfect.
And so just for to add a little detail on the last figure here, it can look like tube, but it is not like tube because it is just a display effect. Indeed, if I only display like the trajectory where the event is guaranteed not to happen, or the uncertain trajectory, we can see that it is not tube. It is really we have all the trajectory that are overlapping, and it looks like tube, but it's not tube.
Yeah, and yeah, this generalization of a tube maybe is somehow related to the things that Julien Alexandre Di Sondretto did with the things that he did with the potential clouds.
Yeah, maybe.
Because there he propagated some kinds of alpha cuts.
Mm-hmm.
Yeah, and approximated then with the help of a set-valued calculus the corresponding ranges that are possible, or the corresponding tolerance bounds. This could maybe help to reduce the computational effort for doing the Monte Carlo simulation.
Yeah, it is heavily computable. It has a heavy computation.
Yeah, but the nice thing is it's easy to parallelize.
Yeah, you're right. If anyone have any question.
Doesn't seem to be the case. Then, thanks again, Damien, for your very interesting presentation. Also, for being so patient to answer questions from 2 guys from Oldenburg.
No problem.
And yeah, the only thing that is now left to me is have a nice weekend to all of you. And we'll see each other again in 3 weeks for the next seminar. And our next speaker will be Meng Zhu from the North China University of Technology. And she'll be talking about event-triggered state interval estimation procedures. From that point of view, again, many thanks for attending today's seminar, and see all of you soon in one of our upcoming meetings.
Thank you, Andreas. Have a nice weekend.